So today is June 15, 2022. It's a great pleasure to introduce Tom Yamashita and Mathew Mate to our oral history series dedicated to the history of digital recording. Doctors Yamashita and Mate have contributed immensely to the field of hard disk drive tribology. Tribology is a science of sliding bodies, which usually involves friction, wear, and lubrication. The reason why it is so critical to disk drive technology is because the magnetic head is riding and sometimes sliding very close to the spinning disk surface under very high velocities of close to 100 miles per hour. In the disk drive industry, tribology therefore refers not only to the reliability of the device, but also the push to lower and precisely control the head to medium spacing known as HMS. During their careers, Drs. Mate and Yamashita have helped reduce HMS from a few micrometers to just a few nanometers. This has enabled over a million-fold increase in storage densities. Dr. Tom Yamashita played a key role at Komag Incorporated, a company that played an important part in the introduction of sputtered thin-film media used in small form factor disk drives, the 5¼ and 3½ disk drives. Tom Yamashita obtained a BS in chemistry and an MS and PhD in material science from Stanford University. He began his career in the disk drive business by joining Komag at its inception in 1984 and worked there until 2007 when the company was acquired by Western Digital. He continued to work at Western Digital until 2012, where he retired. He has developed many of the processes used in the manufacture of thin-film media at Komag, with 34 patents to his credit and many publications. His last position at Komag before it was acquired was Chief Technical Officer, CTO. Dr. Mathew Mate worked for 30 years in the industry doing research and development of materials for nanotechnology and nanotribology applications. He started his industrial career at the IBM Almaden Research Center after completing his PhD in physics from the UC Berkeley in 1986. Later, he worked in the disk drive divisions of Hitachi and Western Digital. He retired from Western Digital in 2016 to pursue other interests, including writing the second edition of his book, Tribology on a Small Scale, and conducting surface science research at Stanford and SLAC as a visiting staff scientist in the Applied Energy Division. Mathew Mate is best known for his research into the molecular and atomic levels origins of tribology, and in addition to this, Mathew has been extensively involved in the research and development of new technologies for disk drives. Finally, a little bit about myself. My name is Bruno Marchon. I was born and raised in France, where I got a PhD in physical chemistry in 1983. My career spans over 27 years in the disk drive industry, starting as an engineer at Seagate. I then held various senior management positions at Seagate, IBM, and Hitachi, mostly in R&D, and developing and implementing new technologies that enabled higher storage densities and improved drive reliability. I would also like to acknowledge Dr. Tadashi Yogi, who helped me put this oral history interview together. Tadashi is also a pioneer and key contributor to the history of hard disk drives. Unfortunately, though, he could not make it today, and he asked me to conduct the interview on my own. I'll try the best I can. Mathew and Tom, welcome. Let us start the interview with you, Tom. Can you tell us about your childhood? Where did you grow up?
So I was born in Kyushu, island of Kyushu, Japan, and a small city called Kushikino. So I was there until I was 10 years old. I immigrated to the United States with my mother in 1965. My father was here 5 years earlier. He came on his own. So we came to join him. I first grew up in Sunnyvale for about 2 years, and then we moved to Salinas, California, where my parents were involved in growing flowers, farming business. And From there, I entered Stanford University, and as Bruno said, majored in chemistry and graduate work in material science. I worked under Professor Robert Sinclair. He was an expert in transmission electron microscopy. That's where I focused most of my attention, specifically on doing very high resolution transmission electron microscopy. It was trying to push the limit of the performance of electron microscope for most of my graduate career, trying to image a near atomic resolution in electron microscope. I did quite a few number of things in that line. I was looking at material called cadmium telluride, which is a solar cell material. And I was looking at various defects and solar cell structures using cadmium telluride. During my early years in Stanford, I was assigned to a project with Xerox Palo Alto Research Center. And there I was assigned to Tu Chen, Dr. Tu Chen. He was developing thin film magnetic media at the time. So I worked for him for about a year, looking at the thin film media that he was producing, basically by transmission electron microscopy. But then I moved on to do this photovoltaic materials, but I kept in contact with him. And because of that, when he started Komag, he asked me to join, and so I joined Komag in 1984. I was the 12th employee, so I was there from the ground up, basically.
Let's rewind a little bit about your childhood. And so you started as a chemist at BS in chemistry. Even before that, what age did you start thinking that perhaps you were driven to have a career in science?
So, as I mentioned, my family was involved in farming, and that's what I did. I worked under my father. We built greenhouses and grew the flowers and sold them all over the country. But my father, the farming was not his choice, and he encouraged me to pursue other things. And I guess I was always fairly good at science, not so much in math, but I was very strong in science. So I think that led me to pursue that direction. So when I entered Stanford, I was fairly quickly got into chemistry, and that was a very good field for me. I didn't know much about material science, but I took the first course that Professor Sinclair taught when he came to Stanford, and that made a big impression on me, and that's how I got into the material science.
Matthew, same question. Where did you grow up? And
Okay. For the first 14 years of my life, I grew up in Columbus, Ohio, where my father was a professor of physics, and my mother taught in the history department there. So a lot of my early interest in physics and science came from during that time when I was in Ohio, and my father was sort of bringing home stuff from the lab and showing me all these neat things, and encouraged my interest in all sorts of technical stuff. Right? We built my own little crystal radio set, and then we'd build little devices from Heathkit and things like that. And the space age was a big thing back then because the moon landings and things. It was a fun time growing up in the 60s in middle America, right? Because so much new technology is coming along, so much social change was going on as well.
But did your father do his own research, and if yes, what field was he in?
Oh, he was a condensed matter physicist. His specialty was low temperature, particularly liquid helium type physics, which is back then was a pretty popular thing. It's not so much popular now. So, and at one point I went back and looked up his little PhD thesis, and it was actually on contact at low temperature. how do you measure contact areas at low temperatures?
Like mechanical or electrical contact?
Mechanical contact. At thermal. His specialty was thermal transport at low temperatures. So he came up with a measure of the contact area at low temperatures due to thermal transport, right? So, and you do what's one of the transport properties of liquid heliums, which have a lot of interesting, behavior. Depending on what type of liquid helium you've got. And so I was always, playing around with all sorts of electronics and science stuff when I was a kid. Had my own telescope and things like that.
Did you have your own little lab in your bedroom doing little experiments?
No, my father had a workshop that I sometimes helped at. He was into carpentry, and my brother eventually became a carpenter. So we both learned from our fathers our own life passions, as it were. And my mother was like I say, was in the history department, right? So I also have a passion for history as well. So then my father actually passed away when I was 12. So my mother had to find a more permanent job. She only had a temporary job at Ohio State University. So she eventually got a permanent professorship at the University of Oregon. So when I was 14, I moved to Eugene, Oregon, and went to high school there, and continued. By the point I decided, hey, I want to be a scientist or an engineer. I hadn't quite made up my mind. So by the time I was in high school.
Were you good at math, physics, chemistry?
Well, I was very good at math, right? So, and the physics came pretty easily to me, right? So I didn't see why everyone else had trouble with it,
So then
the standard geeky stuff that kids are.
Then why Berkeley then?
Oh, well, by the time I was in Eugene, Oregon, I said, I'll apply to the 4 best engineering schools on the West Coast, And in the end, I decided, hey, Berkeley. And I had visited Berkeley and go, hey, this would be a good place to go. Stanford didn't accept me, so I didn't go there. And Caltech, I decided, well, that wasn't really the right place for me. So, so I was an undergraduate at Berkeley in engineering physics, because like I said, I couldn't make up my mind between engineering and physics. One interesting thing that I did as an undergraduate was I spent my junior year abroad at Oxford University doing their second-year physics course, which is a very different type of instruction than the American system. They do a tutorial-based system where a tutor sort of guides you through everything you ought to know about physics. That's what our tutor said. Hey, so that was a very interesting experience. And that sort of solidified me. Okay, I want to really focus on the physics side of for future work. So at that point, I decided, hey, I'm going to apply to do a PhD in physics. And I decided I'd do solid state physics. That's at that time, that was what interested me the most. I think a lot of it has to do with a lot of interest in semiconductors back then and other solid state stuff, and getting interested in materials science as well. And again, I applied to what I thought were the 4 best physics departments for solid state physics, but and I got accepted to all of them, and they said, well, I enjoy Berkeley so much, I'm just going to stay here.
Yeah, so both of you stayed for a PhD in the same.
Well, they always tell you that you go to a different place for grad school, get a different experience. I didn't really see the point of that.
Yeah, if you were one of the best, then.
Well, not only that, but you've been to that time in Berkeley. It's hard to move on from Berkeley. It's very nice, and I've stayed in the Bay Area because again, it was hard to move on from the Bay Area, right?
So then, how did you decide your PhD?
Okay, that got to there is a story behind that. I sort of got past the qualifying stage. The physics departments at Berkeley want you to do that, pass your qualifying the first year through written exam, oral exam, and say, okay, then you go off and that gives you sort of a hunting license to go out for a research group, right? So, and the original person I wanted to work with was Professor Ron Shen, who's a very famous optics guy and solid state physics guy as well, right? When I talked to him, he sort of told me, well, he didn't really have space to take on new students, but what I ought to do is go talk to Professor Gabor Somajai in the chemistry department. Because he had talked about collaborations with doing Gabor, and also the part of Ron Shen's work that most interests me was the use of using laser diagnostics to study surface science phenomena. I started getting interested in surface science as the interesting part of solid state physics I want to concentrate. And he goes, well, once I mentioned that, he said, go talk to Gabor Somajai, because he's like the top person in the surface science field and likes to bring on physics graduate students, a couple of physics graduate students. So, and so I went to talk to Gabor Samardzai, and for those who, my first impression with Gabor Samardzai is this guy is so enthusiastic, it's just bundling energy. I just really liked the way he thought and sort of expressed himself and the way he thought through science. That first meeting was very pivotal for me in terms of being sold on working for Gabor Samardzai. Now Bruno knows Gabor Samardzai very well. You also see on a good day he's fantastic. On a day where he wants to disappoint you with he's very rough.
Yes, yeah, he drives these people hard. Yeah.
Yeah. Very colorful language at times. At least back then, I don't know. He's much more mellow nowadays,
And then he suggested you work with hydrogen on surfaces or something?
No, that came later. I mean,
later. Okay.
When he said at that time, and I think for a long time, as part of an ongoing program, what are the structure of molecules on surface? Structures of the surface atoms, what's the structure of molecules on surfaces, how do they bond to surfaces? And there are various ways he did that in the group. One was low energy electron diffraction, analyzing the what they call the IV curves, the sort of doing, basically using electrons to diffract and get crystallography out. But in addition to that, he was also ramping up his vibrational spectroscopy work, doing low energy electron loss spectroscopy at high resolution, right? So he sort of said you really needed some more people to do the high resolution electron energy loss spectroscopy, to do the vibrational spectroscopy, to sort of establish an initial guess what the molecule structure was, to tie into the low energy electron diffraction work. So that's where some of my focus was, and I was initially, right, was on doing high resolution electron energy loss versus first working with one postdoc who already had a system set up for that, and then building my own system up, a new system that would do that in my own project. And once I got that up and running, it's sort of like, well, you clean the surface in ultra high vacuum, get them nice and atomically clean, dose it with the molecules, take the vibrational spectra, write out the paper, and publish it. And that got Gabor very happy because you could generate papers very easily that way, right, in publications. And you made me more happy when I discovered that you could, by introducing CO molecules into the system, I could order certain molecules like benzene up he said that's fantastic because now I could do the lead crystallography on these structures. And we had a good idea from the vibrational spectroscopy what they were going on. So that was sort of my big discovery as a grad student, an ordering agent for the low energy electron spectroscopy. Also during my thesis work, Gabor also kept telling me is how one of the frontiers for surface science was tribology, how friction lubrication work, because that's where two surfaces come together. It's a buried interface, so it's very difficult to probe. How do you understand, let's say from the molecular structure, how that affects, say, lubrication? So, and then I sort of thought, hey, that is a great idea. So, if you're going to be a famous scientist, it's best to go off and work in a field where not too many other people are working on, right? So, and while there was a lot of people doing, say, lubrication work or wear work, they're all sort of not doing it at the molecular level. And Gabor said, hey, do it at the molecular level.
And that's what started it all. So we'll get back to this later on. But so, Tom, you also worked in vacuum during your PhD with electrons, although the energy level was quite a bit different. So tell us how you chose Professor Sinclair and this research topic.
So Professor Sinclair was still very early in his career at Stanford, and he wanted to do electron microscopy. So first thing he did was to purchase this very expensive electron microscope, and his main effort was to push the resolution of the microscope to the highest level possible. But you needed material to look at, and it turned out the cadmium telluride was an excellent material, very heavy, high contrast in the electron microscope, and it had a very large lattice constant, which made it easy to image. Compared to everybody else was working on silicon, which is actually quite difficult. So those two things kind of came together, and he basically let me have a free rein on this brand new microscope. Probably cost over $1 million back then, and I was able to spend a huge amount of time to push the instrumentation to the best possible, and started to get these fantastic images of atomic structure defects. And we hooked up this video camera, and we could actually see defects in motion. These are dislocation, crystalline structures, crystalline defects in cadmium telluride. And I don't think it's never been done before to the extent that we did. And so he took all these movies that I took, and he went to all the conferences, and it was a big hit.
Did you publish in some
he showed them all over the place. So that was good for me too. But very appreciative of Bob Sinclair to give me that kind of access to this fancy instrumentation. But I did get a lot out of the equipment.
And how did you get involved then with the Xerox PARC team?
Now that was something that before he got going on this high-resolution electron microscopy, I was just starting as a master's student. I needed a project, and Bob Sinclair was just by happenstance was assigned to me as an advisor. And so I said, Bob, I need to do some work, to get my feet wet in doing scientific work. So he had a strong connection with Xerox PARC, and gave me this project, which happened to be looking at thin film media that Tu Chen was working on. Xerox PARC, by the way, back then was an incredible place in the late 70s. They had this Alto computer.
Alto, yeah.
Alto, and they were developing Ethernet. They had laser printer. They even had a color laser copier, which was, never seen anything like it before, And I think about 2 years later, Steve Jobs came through and took everything.
Saw the light. Did you see all the bean bags and Xerox PARC?
Anyway, so that was a very, very interesting experience working for Tu Chen. So I learned how to all about how the magnetic recording is done. I learned how to use VSM, for example, vibrating, sample magnetometer, those kind of things. So Tu Chen showed me a lot of things that I didn't know about, and that's why I learned magnetic recording in a way. But I didn't stay with it for too long, only about a year. And I moved on to focus on electron microscopy, but Tu Chen would call me up every so often and say, I want to look at this, and so use the TEM to analyze films for him.
Did you publish anything with Tu Chen then?
Yeah, several papers.
Several papers.
So it was a good experience for me. And we also shared the love of fishing. So he would take me out fishing, and so that was another connection.
Okay. So we're going to get close to the disk drive industry now. So go back to Mathew now. So Mathew, then you mentioned a little bit about your early interest in tribology and using surface science tools to understand the molecular or atomic level of tribology. So could you tell us a little bit about this and what led you then to the IBM
Okay,
postdoc?
yeah, I mean, the story there is that one of the things I worked on when I was finishing up my thesis work at Berkeley was you could bore so much. I was interested in getting into the field of tribology, so he had me build a pin-on-disk tester or pin-on sample tester in UHV, right? So I think I got that sort of built and demonstrated might work, and then I left with my thesis. But while I was building, I'm going, this is not really the way to do it to get a atomic resolution. The way to do it is use some sort of scanning probe to do it with a very sharp tip where it latches a few atoms there and measure the forces on it. This was before the invention of atomic force microscope. I was sort of turning around these ideas in my head going, really, I ought to invent the atomic force microscope. But I didn't realize that Gerhard Benning and Cal Quate were already in the process of, were about 6 months ahead of my thinking on this, and we're just about to publish that.
The STM. Or the AFM?
STM was already out.
STM
right.
was already
so
out.
I knew what the STM was saying. I need something like the STM, but where you can measure the force on the tip. And I even talked to a professor in the electrical engineering department how you could do that with microfabricated cantilevers, which is very ahead of my time, I think about it, back then, right? So I would have been much more famous if I had started my PhD thesis on this rather than thinking about it in the last 6 months of my PhD thesis, or last year of my PhD thesis. But what my thinking was, well, I don't have time to do this on my PhD thesis. I ought to get a postdoc to do this. And I thought the place I really like to work is at IBM Almaden. And I had actually done a summer position there doing perpendicular media recording back in '81. So way before perpendicular media came out. So I knew the people at IBM Almaden, and they're going, that's a great place to work, right? So, and a friend of mine, Shirley Chang, who had graduated from Berkeley a few years before, was at IBM Almaden Research Center. So I called her up and said, hey, I'm looking for a postdoc position where I can do something like, build this probe that measures the forces on atoms. And she goes, well, we just happen to be looking for a postdoc to do that project. Because she knew about the Gerhard Benning and Cal Quate thing, because Gerhard Benning was an IBM employee. And she was working with Gary McClellan, who was getting responsible for tribology at IBM Almaden Research at that time, with a few other people. So they brought me in for an interview, hired me pretty much on the spot, and I went to work there as a postdoc. But by this time, Cal Quate and Gerhard Benning had published the first paper on atomic force microscopes. So, they always demonstrate how it could be done, and the issues there. And we decided, and particularly Gary McClellan had some very clever ideas of different ways of building an atomic force microscope. We built one based on optical interference that we then used to do measure the first atomic scale friction forces, right? So that was the thing, Gerhard Benning had measured the forces acting normal to the surface. We measured both the normal forces and friction forces and built the first microscope to do that. Scanned it over graphite, got atomic scale friction, and voila, I'm a famous guy in the atomic scale tribology field.
There was a PRL.
Physics Review letter.
Yeah.
And it's the only time that's ever happened to me any paper. I submitted the publication. A month later, they called me up and started saying, we're going to publish this as is. As is. Never happened to me ever before.
Any other time.
Any other time,
Right. So that was the very first time that people put a strain gauge to measure the lateral force.
It was by optical interference.
Okay.
But for those of the people who are familiar with strain gauges, it measures the strain, the displacement of the thing there. We did a very crude sort of optical interference setup. There are much more sophisticated ones that we came up with later at IBM Almaden. And now they do it all by beam deflection off the microfabricated cantilevers.
Excellent.
So that's how I got into IBM Almaden doing tribology research. And then after about, published many of and that was a great time to do atomic force microscope, because whatever you did was an exciting new result. You were the first guy ever to do it. You publish a paper and everyone goes, oh, wow, that's great and wonderful. But eventually, your postdoc it's going to come to an end. You got to go, well, I got to get a permanent job, right? So, and I happened to run into Brian Street, who at that point was a department manager at IBM Almaden Research, but in what they call the storage function. That's the part of IBM Almaden Research Center that did the research for the disk drive business, right, at that time. And he was the department manager for that part dealing with the tribology issues, the head disk interface issues, and the magnetics of the disk media part of it. And be out with lunch, and I said, hey, I'm looking for a job in tribology. And he said, well, we happen to be looking for people to hire in tribology. So that's, he basically was the one who pulled me into as a permanent employee now of IBM Research, into the disk drive tribology research business for the IBM's disk drives.
So you, Tom, tell us a little more about your interaction with Tu Chen and what was important in the research he was doing at Xerox Spark, and how did that research, they thought, could apply to magnetic recording?
So, let's see. He was, fairly early on, he was doing things like magnetic bubbles, and so he kind of went through the motion of looking at various technologies. Certainly perpendicular recording, he was heavily involved in that. But somewhere he decided that that you could start a business, and it would have to be longitudinal recording. And he was working on a material called cobalt-rhenium system to make recording media out of it. And somewhere during the time that he was at Xerox Spark, Xerox was trying to create this new business, Office of the Future. And that involved the auto computers, and storage system. They bought this company called Scientific Data System, I believe, I don't know, for like $1 billion or something. And they had a storage division too. So he was trying to make an actual device for their product line.
So the disk drive already existed?
Yeah, they had a business already. I think it was called Century Data, and they were making oxide disk packs, for this computer division that they had. And you've seen the auto computer. He had this big oxide disk pack. You just slide into the bottom of this computer, and he had the operating system, storage, 10 megabytes or something. So they wanted to improve the capacity and performance of these kind of drives intended for this Office of the Future. And it had to be thin film. That's because it's the only way you could get the recording density. So he had this idea to do all of that, but somehow Xerox kind of lost their way and decided to just cancel everything, kind of forced them to consider going into a business of his own. And so 1982, 83, he started to try to formulate a business plan to start a company to make hard disk media. And
was thin film media already existed, but it was plating technology, perhaps?
So around 1982, 3, the plated media was already starting to be being used. The plated media actually goes back a little further. It was used for things like instant replay machine made by Ampex. Those used plated media, I believe. And so the first thin film media was all plated, and the 5 1/4 was the format that was going to be used in PCs and so on. So by the time Komag has started in 1983, 84 timeframe, there were already many plated media companies. But the kind of film that the Komag was trying to make, this was by sputtering. It was considered maybe a little bit too expensive compared to plating, so there weren't very many, but there were already several going by the time Komag has started.
So it was thought that perhaps the performance was going to be better, but the cost maybe not so much.
Eventually. So the plated media, the capacity must have been like 5, 10 megabytes, at most. But there was a limit to the coercivity that you could get with plated process. So there wasn't much of a pathway to get further. So I think Tu Chen saw it correctly that the thin film media was the way to go. You could create, use all kinds of different alloys that has much more higher coercivity and hence more higher recording density is possible.
So before we go deeper into the technology now, I think Mathew, you've prepared a little tutorial, and perhaps you can tell us a little bit about what the technology involves.
Let's start off with this demo here. I'm going to hold it up near my head here so people can see. And I guess this is the inside of a disk drive. I just pull the cover off here. And the way a disk drive works is you're storing information on a magnetic film, which is on this disk surface. That's why it's called a disk drive. And this disk rotates around. And as it rotates around, there's a... Okay, let me back up here. And this, like I said, stored magnetically on the thin film on top of the disk surface as ones and zeros. Those ones and zeros put out little magnetic fields into the air above it. To read those magnetic fields, there's what's called a recording head, which is located, I don't know how well you can see this, right at the end of this long suspension going out here, on this thing here. And that's reads the magnetic fields that are going across there. So that as the disk rotates round and round, this actuator here puts that recording head back and forth across the disks so that you can read and write the information that you want to be stored on the disk drive there. And this is explained a bit more on the slide I've brought with me here. And again, on the left here side of the things, again, that open view of the disk there. And from the arrow, you can see that's where the illustrates the disk rotation that goes around underneath the recording head. That recording head is mounted on the trailing edge of a slider, which is shown in part B here. And that slider, the bottom of that slider, as shown in image C here, is what's patterned with what they call an air-bearing surface. That air-bearing surface is designed so that when the disk rotates, it pulls air underneath the slider. That air interacts with the air-bearing surface to cause the slider to fly over the disk surface. That's a very important function because that flies, it gives a bit clearance between the head and the disk. So hopefully most of the time the head does not contact the disk surface. And the reason why that's important is this disk is spinning around 5400 RPM or 7200 RPM. And that means the linear speed can go up to 100 miles an hour like Bruno was saying here. And so you don't want any contact between that head at 100 miles an hour. So if you can fly it up some distance, you can minimize that contact. But contacts do happen, and that's where all this tribology come important here. Because when they contact, you've got friction, you've got wear, you've got adhesion. And as Bruno mentioned, the word tribology means that study of friction, lubrication, wear, and adhesion, right?
So what's the distance between the head and the disk?
Well, that's a...
Oh, you're going to bring that up.
Yeah, okay. I'll talk. I think I'm done with this one. Yeah, but the point I want to make, last point here is what's mentioned here at the bottom here, is if you have too much contact, you got too much friction and wear, eventually the thing will fail. And we used to call it a head crash. Basically, the head would just crash and the disk would turn the power and kill the drive, and whoever owned the disk drive would lose all the data that was stored on there and be very unhappy, right? So they go off and buy their next disk drive from someone else. So you wanted to avoid that, right? Those head crashes. So that's why tribology is so important to the head disk interface. And that's I tell people that's why people pay my salaries, so that we make a more reliable disk drive. Okay, on the slide number 2 here, on the let's see what this is. Left-hand side is again that image we were showing before of the cutout of what inside a disk drive looks. The inset here shows that recording head and slider flying over the disk surface. And as it flies, I don't know if the animation works on this, there's a little bit of flutter on there that you can sort of see vibrating up and down. So the issue is, okay, if it flutters too much, then you're going to get a contact with the disk surface. at 100 miles an hour. In today's drives, this clearance is less than 2 nanometers. It's very small. Whereas, as a plot here on the lower right shows, is that it used to be much higher. It used to be about, like Bruno told me the other day, was just over 20 microns in the first disk drive shipped in 1956. So over the years, they've sort of reduced this down to less than 2 nanometers. And the reason why they're doing that is because over time they've been trying to get more and more bits onto the disk surface. And the reason why that is the first disk drive, the RAMAC in 1956, only had 3 megabytes of data stored on 5? I think it depends on which model you're talking about. 5 megabytes, let's say, and the size of about a small refrigerator. Which nowadays, the small mobile drives can hold, terabytes of data. It's a very impressive improvement over the last almost 70 years now, right? So, and as they got more bits down there, the magnetic fields have gotten close to the disk, so you've got to get that recording head closer to the disk to be able to get the read and write those high areal densities, right? So that's sort of driven this clearance go down to below 2 nanometers. In today's disk drive, it must be around, I don't know, Bruno, maybe you know this number. What is it, like 1 nanometer or less now? Less than a nanometer, which is just a few atomic distances thick, right? So a clearance gap.
So by the way, Matthew, was 5 mega characters for the RAMAC, but the character was 6 bits. So it's actually 5 mega characters at 6 bits each is actually 3 megabytes. So
okay. That's what's confused me probably. For those people who don't know what I have no feel for a nanometer is, right? One way people will do in the disk drive industry is they scale up. You say take that slider with the recording head on, scale it up to the size of a jumbo jet airplane like the 787, and then say how close do I have to fly that to a surface, scaled up distance to match the 2 nanometer clearance. It turns out to be about 0.05 millimeters, or about 50 microns, which is the width of a very thin human hair. So you think about a big jumbo jet trying to fly over the ground with a clearance of just the width of a very thin human hair. Okay, so let's talk about slide number 3 here. Again, there's this concept of head media spacing that Bruno mentioned a while back. And as I was saying, to get the high areal densities, you want to get the recording head as close as possible. The critical parameter there is this head media spacing, which is, as illustrated on the right side of this figure on the right side here, is the distance from the bottom of the sensor in the head that's going to do the reading and writing of the bits on the disk, and the top of the magnetic layer on the disk surface, right? So that's the head media spacing. Now the problem is for, like I said, the problem is that this magnetic media that's on the disk is actually fairly soft, and you've got this recording head flying over at 100 miles an hour, let's say. And so if you have contact of on that soft magnetic media, you're going to get a lot of severe wear. So what we've done in the disk drive industry is coat it with a hard material, like a hard carbon overcoat is like the standard one nowadays. And that provides a lot of protection against the impacts that can happen when there's a hard carbon overcoat. But it's not enough. They also then put a monolayer of lubricant on there as well to further protect it and give it, so you can last through there. And today's recording head sliders also have a monolayer of, not a monolayer, thin carbon overcoat on the head side to protect the head side as well, because that magnetic sensor that's on the head is very sensitive to impacts and corrosion as well. So you've got both sides are coated there. But all those thicknesses from the overcoat, the lubricant, and also the roughness of the disk play an important role on which is used for the tribology, add up to have to fit in that very small magnetic spacing. And if you look at the plot on the left here, that's been going down steadily over the time period here is from like 1980 to 2010. It's been systematically going down to 10 nanometers in 2010. So that means all your carbon overcoat thickness, lubricants thicknesses, and clearance and roughness must all fit in that magnetic spacing budget. And I think since 2010, this whole thing has sort of plateaued out a bit. It's very tough to get much more improvement now. So it's sort of fallen off the straight line on this semi-log plot. But you're still getting down to 10 nanometers head media spacing has been very impressive, because that means the clearance, like I was saying before, has to be less than 2 nanometers. The carbon overcoat thicknesses are getting down to just a few nanometers. Lubricant thicknesses are just one layer of molecules lying flat on the surface. The roughness had to go down from where it was before, and I'm sure we're going to talk about roughness here in the future, right? So that's systematically coming down here.
Yeah, and I guess as a tribute to people like you, not only all the dimensions have reduced dramatically, but the reliability of a disk drive has improved dramatically over the last 30 years. Right? 30 years ago, it was not unheard of that your disk drive would just stop working in your computer, but today disk drives are extremely reliable.
Well, one thing I want to point out is, you notice how this is a nice linear plot, here, and the reason why that is it's not due to any technological thing. More of a marketing guy. The people in marketing said, hey, 2 years from now you have to make a disk drive product that has twice the areal density, and that meant the magnetic spacing had to go down a certain amount, and no matter how good a job you did on the last disk drive, well, you got to do twice as better 2 years from now in terms of improving the area density, and preferably improving the reliability as well. So there was always a big pressure to, great job last time, now do better next time.
Could you tell us a little bit about some of the failure mechanisms of a disk drive? You mentioned a head crash. Were there other failures that you had to deal with? People mentioned stiction, for example.
Well, that's on this disk drive here, this is a powered off disk drive, so the head is sitting on the disk at the ID, and there's actually a texture zone here which has extra roughness to prevent this phenomenon of stiction, which is basically if there's too little clearance between the head and the disk where it's sitting, all the lubricant will wick up around the head and cause big adhesion problem, and so much friction force that you can't start the drive up again. Basically, this thing can't spin because there's too much friction there between the head and the disk due to lubricant wicking up in the small gap. So there are all sorts of texturing schemes were put in to minimize that sort of stiction problem.
And I guess we're going to talk about that later, but some of your job was also to understand the atomic nature of that.
All the physics
friction.
of the lubricant. And you're talking about other failure mechanisms. One was, which it didn't cause a head crash, was lubricant pickup on the slider, which would then coat the slider with a thin film of lubricant that would raise the fly height, lose your magnetic spacing, and then the drive wouldn't be able to read the data anymore because you're flying too high now, right, because of lubricant pickup, right? So we also try to understand how did the lubricant get from the disk to the slider, right? And we also had problems with lubricant spin-off, because we should make the lubricant too thin. A whole range of funny lubricant issues. Lubricant degradation from incompatible materials in the disk drive.
So Tom, we just talked about some of the failure mechanisms in these drives, and I think that's something that you've experienced as well in the early days at Komag. You told me that you didn't go to tribology by choice, but by necessity. So can you tell me a little bit about some of the early experience at Komag and some of the problems you guys were facing in the field of tribology?
So when Komag got started, there was sort of a specification out there already because the plated disk was out there, and of course the so-called CSS drives, contact star stop, was pretty well established. The market that Komag was going for was this small form factor, 5¼ inch. And it was clearly intended for like a PC market. And there was this requirement of 20,000 star stops. Basically, you turn on the drive several times a day. It's supposed to last 10 years or whatever. Every time you turn on this drive, the head will actually land on the disk. So the motors that these small form factor drive had was not very powerful. They were relatively cheap and didn't have so much torque. So this contact start-stop requirement had built into it a requirement for a friction force that was specified, so that the motor can turn on. And if the disk was starting to wear out, for example, the friction force would build up eventually, and you wouldn't be able to turn on the drive. So this 20,000 start-stop cycle is actually quite challenging. Certainly the earlier drive, the first 5.25-inch drive was made by Shugart, and it was starting to be put into a small computer system, including PCs, and they clearly met those kind of a requirement. But the thin film couldn't get there initially, and so that required a lot of innovations to make it last this 20,000 cycles. The testing equipment needed to do these kind of tests was fairly in infancy also. So it was difficult just to measure. You could put them in the drive and test it that way, but that wasn't really available. So we had instrumentation problems as well to test it. So anyway, so this 20,000 contact stop cycle was an issue, and another issue was the drive environment itself was relatively poor. Literally, the motor was leaking oil. There were various material that were outgassed inside the drive enclosure, and when the drive is running hot, things would outgas, and these things could react with the lubricant. Many things happen between the head and the disk. A muck could build up between the interface between the head and the disk, and this would compromise. If it stopped flying, like Matthew said, you could have a head crash. So those were some of the parameters, and then it's not really tribology, but the other issue was corrosion. The thin film disk, particularly the plated media, was very prone to corrosion. And so in the drive environment, if a corrosion occurred, you could have these corrosion byproducts that will actually protrude out of the disk surface, and that will also muck up the interface. So these were some of the issues that we were dealing with initially.
So Komag, as a company, started straight into making sputtered thin film. Were you guys the first ones to do this in the industry?
I don't believe there were several companies already trying to do similar things. So I don't think we were the first, but we certainly were the first to actually put on the market a disk that worked to meet these 20,000 contact stop cycles.
Who were your first customers?
Most of them are no longer around. There was a company called Vertex. Priam was another one. Maxtor was already starting to ship many products.
Did Seagate buy from?
Seagate, Quantum, and there were just a host of bunch of smaller companies. Also, there were the big players like the DEC and IBM, Control Data, those companies were starting to put thin film disk. I believe most of it was initially plated disk, but certainly they themselves were working on sputter films. So I don't think we were the first one, but I do think that Komag was first to really make a sputter thin film disk that had all the components. It had the 20,000 CSS cycle. We achieved that by putting a lubricant successfully on it. The stay put, as Matthew said, it can spin off, it could just wear out. All of those things can happen, but we were the first to be able to get a real disk that actually met the specification.
And I guess at the time, molecular tribology was still in its infancy, and people didn't really have the understanding of friction and wear processes that was needed to understand all this. So, did you rely mostly on empirism and just trial and error, or?
A lot of trial and error. We couldn't even measure the thickness of the lubricant, so it was basically. We had this jig at 10 gram weight, which we glued the head to, and it was dragged across the disc with a string. And at the end of the string, we had a strain gauge. And so work out the math, and you get a 10 gram lateral force, and that defined the stiction requirement. So that was a kind of a quick way to test. But we did have a contact start-stop tester that had it was a very specialized strain gauge setup. It was an octagon-shaped copper ring, which I think had a 4 strain gauge attached to it, and it can. And at the end of this was the suspension with the head, and we would mount the disc and run the start-stop on this. And the strain gauge was calibrated to measure the friction force while it's running, and then the start friction to dislodge it out of the surface of the static friction. So that was actually I think it came right out of IBM. 2 of our founders were from IBM, and one was a mechanical engineer. His name is Jim Shear. And I think he worked on a lot of the tribological problems at IBM. So it was the person that was most familiar with these kind of issues. Tu Chen, on the other hand, he had no knowledge of tribology, very little, and he developed all the materials, the things like overcoats, things of that nature.
So Matthew, early time at IBM,
Okay.
so you moved to more of a product.
Yeah, so I moved to the storage the function of IBM Almaden Research Center, which their goal is to do the research for future disk drives, right? And my boss, Brian Street, said, okay, he wanted me to focus on lubrication on thin film media, right? And he was also happy to have me continue to do atomic force microscopy as work. So I started using the atomic force microscopy to study lubricants on disks and particularly thin film media. And one of the first experiments I did was sort of just bring an AFM tip into contact with the disk surface. And when you bring it into contact, you get a little force down when you first touch the top of the lubricant film, and you can detect that little deflection there and calculate the viscous force that's acting on as the lubricant wicks up around the tip. And then when you go through, you can push into hard contact with the disk underneath it and get a nice strong repulsive force. And what I kind of realized very early on, you can kind of measure the lubricant thickness this way by when you first touch the top and when you first contact the hard wall there. As Tom was saying, one of the issues is how do you measure that lubricant thickness, right? So I say, hey, the AFM can do that. And we had a way of correcting for the amount of lubricant that gets transferred to the tip, so we could correct for that. And it happened to be one story I have is one day I was in the hallway and I ran into my third line manager, who was responsible for all of disk drive research. And he asked me what was going on. And I said, oh, yeah, I came up with this fun little thing that I'm working on in the lab. He says, oh, that's a great idea. Instead of thin film media, you ought to do that on particulate disks. And we really want to know what the thickness is on this particular product that we want to ship, but we're having problems with, right? So I got switched over from thin film media into studying lubricants on particulate disks. And,
so particulate was the oxide.
Yeah, so what particulate media is iron oxide particles. The magnetic information is stored in iron oxide particles, which are magnetic. And they are bound together by a polymer which was designed to be very porous. And the reason why it was designed to be porous, because then you could sort of load up those pores with lubricant, because they really want to have as much lubricant as they wanted on these disks. And they had particularly designed this thing to have a porous magnetic film and an even more porous anodyne layer underneath it, which could hold a lot of lubricants. They had measured the amount of lubricant on a disk in milligrams, and the way they would decide how much lubricant was on the total disk was by weighing it so many milligrams, But they didn't really, so they knew all this pore, they had, if you worked it out in terms of angstroms, it was like 1,000 angstroms of lubricant. But they knew that all of that wasn't on the surface. They really want to know how much was on the surface of this porous media. But all their measurement techniques would sort of give them a big background from the stuff that was in the pores there. So I used the AFM microscope to sort of tap my way across the surface, measure the distribution across the surface on the various particulate disks they were interested in. And I showed that on particulate disks of that time period, which was about 87, 88 at that point, 1988, it was about, when it was new, it was about 50 to 70 angstroms, because there was quite a bit of variation there. And then over time, it would spin off to about 30, 40 angstroms, which is still quite a bit of lubricant things. So it was one lubricant molecule is like a radius or diameter of gyration, at least when it started off. And the reason why this the functional man was so worried about this is they found out if they didn't put enough lubricant on there, they would have problems. They want to know what the loop thickness is of these stress drives, because they would fail the stress test. And one other thing I started working on at that time, which eventually tied into this problem, was okay, when this tip comes down in contacts, you get this meniscus force, so you can work out what the meniscus force is on there and go from capillary action pulling up around the tip. But I was curious, well, what determines that meniscus force and how much lubricant is there? And I go, well, that's kind of balanced by the disjoining pressure of the lubricant on the film. And I didn't know what the disjoining pressure was at first, but I figured it was some sort of force that the lubricant molecule feels with the underlying disk substrate, which is like mostly van der Waals forces back in those particular lubricant systems. So you'd have those van der Waals forces trying to pull the lubricant onto the disk. When the tip comes in, you have the capillary pressure going up and making a nice meniscus. And there was a balance between the two, which explained a lot of the physics of how this tip interacted with the surface. And also, once the slider landed on the disk, it would explain the stiction forces that we're seeing, the adhesion forces that we're seeing.
Yeah, and this is when Seagate then read all the nice papers that you
eventually
wrote.
Published, and you actually did a nice job of along with Jim Gui solving.
There's physics in the stiction problem.
You actually work out this analytically. On the porous particulate media, it was the balance between the shape of the pores and the lubricant that was on the surface. And you could show that, hey, actually you have fairly flat profile as you spun off lubricant. You maintain your lubricant thickness because lubricant would come out of the pores until you got to some critical point when the lubricant thickness would drop dramatically as you lost lubricants within the pores, and the capillary pressure in the pores would go away. And that's really what impressed my functional managers, that, hey, we could actually do science on this problem. We can actually understand why this product was failing the stress test, and that the stress test was over stressful, and that they could ship the product and not worry about failing the stress test.
So was IBM still shipping particulate media then?
Yeah, this is pretty much the last, what they call it, they're shipping it in mainframe computers, right? which was when I joined, there was they're shipping what they called the 3380, and then the last sort of mainframe large disk, I think it was the last 3390 was the last one, and that's disk size was 11.5 inches, which is down from the 14.5 of the 3380, right? So you had this pretty big, large, heavy disk and a pretty large enclosure, right? So, and I think at that point, 1/3 of IBM's profit came from selling those 3390 disk drives. So it was a big deal when I sort of said, hey, I understand the science behind this problem. You're having this product that you want to ship, that you're hoping for make so many billions of dollars of profit every year off of.
So Tom, back to Komag. So we understand a little bit about lubricant and stiction. And also the topography of the media is important as well. So tell us a little bit about how you guys controlled, the texture, the topography of the media, right, and also in relationship with the lubricant.
So as Matthew was saying about the particulate media, you have this huge reservoir of lubricant in a thin film media. You just got the hard surface, so you can't put very much lubricant. So there's a phenomenon where you could see this very easily. You put two smooth surface together with liquid. Take a plate of glass and put it together with liquid water in between. You cannot separate these two glass plates. Mm-hmm. That's the stiction effect. So the same thing happens if you put a smooth surface of the head on top of a smooth surface of the disk with a liquid lubricant. You gotta somehow arrange it to separate the two. And the way that's done is to put certain amount of roughness on the surface of the disk. And so that was the initial challenge for Komag, how to put that roughness so that you could still have the lubricant there and keep the head off the surface from this liquid from wicking the surface between the head and the disk. So the substrate that we used, this is for still true today, is starting out with a base aluminum substrate, and on top of that there is a plated nickel phosphorus alloy that was plated on it, and then this is polished because as plated is too rough. So we have a polishing machine to planarize it and then make the surface smooth. So this is something that Tu Chen came up with. At the very last moment of this polishing process, he put a slightly rougher slurry so that you end up with a sort of a scratch, and the scratch is enough to separate the head and the disk. So that allows you to put lubricant on it. So we started that way, and the lubricant that we started to use was basically a same type of lubricant that was used on oxide disk. These are, I guess, Krytox family. Krytox is a brand name for DuPont, and it's a perfluoro polymer, molecular weight of several thousand, very long chain molecule, fantastic lubricant. I think it's used in vacuum grease as well.
Yeah. IBM uses Formulin YR was what we use, and the key feature is it's a linear chain but actually with branches off of it, right? So those branches really help protect the ether linkages with it.
And it's a fantastic invention as lubricant goes. Yeah. It's used in even satellite space applications and so on.
I think that's why we chose it in the disk drive industry. People say, hey, this works pretty well in satellites. It's non-volatile. That's another key factor, right?
Very low vapor pressure.
Very low pressure. Very chemically inert. That's another key factor, right? Because slider hits this with 100 miles an hour, you don't want degradation of your lubricant molecule. If you don't do it right, you've got degradation going on. Right? The problem with hydrocarbons is they get frictional oxidation due to contacts.
So anyway, so we took care of the surface roughness that way and put this Krytox lubricant, which is there's a term called polar versus non-polar lubricant. These long chain molecule, you could put N groups at the end of these long chains of molecule, and when we say non-polar, it means that it doesn't have chemical N groups that cause things to attach more strongly. So the type of lubricant that these Krytox that we tried first were non-polar lubricant, and when we did that and started to do contact start-stop test, we couldn't make 20,000 cycles. I think they were just flowing away. So somehow it needed to be more strongly adherent to the disk surface. Now, back then things were rather hand waving, and there really wasn't any polar lubricant per se. And so out of trying a bunch of these kind of existing lubricant, out of desperation, Tu Chen talked to, or his partner, Jim Scher, talked to this supplier of this lubricant. We were getting this from Montfluos. It was a division of Almaden in Italy. And they were making this lubricant, and I think their trade name was Fonbelin.
Fonbelin YRs with the Krytox.
Yeah.
Krytox is made by DuPont.
Fonbelin was the trade name for the Almaden.
Almaden, yeah.
And today Almaden is purchased by Solvay, so there's Solvay and DuPont sold their business too, I think, spun it off. Anyway, so Jim Scher contacted Almaden, Montfluos. Do you have something else? And Tu Chen, I remember seeing some scientific paper 2 years back that talked about polar lubricant that had, I think it was the OH group or something that caused the lubricant to bond more strongly to the disk. And this is a paper done by NEC at the time. They were doing this on plated disk, and they reported some very, very good results. So Jim Scher went to Montfluos, do you have something similar? And said, we got one. It's called Zedo, and it wasn't even intended for disk application. I think it was meant for some space application. They had a small jar of it. So it was ordered. We paid very exorbitant airfare. As soon as he arrived, we put it onto the disk, and lo and behold, it worked. So that was the key, to put a polar lubricant to get some amount of adherence between the lubricant and the disk, because as Mathew mentioned, there's no reservoir. So that was a kind of a eye-opening realization, and so
the whole industry followed suit, right? Because Zedo became the de facto lubricant.
Became the type of lubricant, So I think after that, people started to really look at, well, how do you measure the amount of bonding? How much is sufficient? Obviously, you can't have everything bonded, right? And even the how you measure it was a problem. You could use different solvents and you get different numbers. So that was kind of interesting.
Mathew, tell us about what lubricant was used by IBM then.
Well, I mean, like I was saying, when I was doing particulate media, there was they were actually trying to decide whether they could go to a Fonbelin Z backbone, which is without the branch groups, and they had a lot of problems with that on the particulate media. And the reason why they had problems, it was interact with the aluminum oxide particles in there that caused lubricant degradation. So then they switched back to formula Y, which with the branch molecules, which the branching groups would protect the ether linkages within the formula backbone. But we had the great thing about the particulate media is you had that big reservoir you could spin off forever, right? Because you never empty out the reservoir because the capillary pressure would sort of hold it within the pores enough for you to keep it on the disk. But when you go to thin film, then you go flat, and you have to start worrying about spin off. If you don't have the functional groups, it'll spin off very fast, and you lose all your thing. And also, you have a lot of mobility, so you get your stiction problems very quickly if they're going to happen, right? So people talk about ZDOL is what the standard came to be. At IBM, we were exploring a lot of them. The AM 2001, which is another Z backbone with a different group. Various sort of denim molecules, denim SH, which has only a functional group at one end. That had a lot of advantages, but in the end didn't work out. I'm trying to remember of other functional groups that we looked at ones with acid end groups. The Z-DAC is what the name for their, and actually IBM for a while were actually shipping product with the stearic acid was the lubricant, which they had a reservoir there that would vapor deposit onto the disk. But that vapor deposition had a lot of problems. But they managed to ship working drives with that back in the mid-'80s and early '90s.
What technique did IBM use? I know Komag will, maybe Tom will discuss that, but was using a different deposition technique. Did IBM use a dip?
For thin film media, as far as I know, is always you dissolve it in a solvent, you dip your disk in it, you pull it out, and it sort of pulls out a thin film of the solution with the lubricant dissolved in. And initially, it was Freon was the solvent, right? And the Freon would evaporate and leave behind the lubricant. Eventually, Freon got banned because of its effect on the ozone layers. They switched it over to trying to remember.
Virtual.
Virtual was one, and there was another one where IBM used.
HFE.
HFE is probably the one I'm thinking. Yeah, you're right. You remember these better than I do.
PF5060.
PF5060. That's the one I think was the most. In my lab, I had them all, so because I was playing around with all these things. But the PF5060 I think was the final choice, right? So, and that was reasonably environmentally friendly, and that was a nice, simple, low-cost way of putting it down. When we looked at all sorts of things like vapor deposition and vacuums and putting drops on them, wiping them down. And that's where the particulate media do. You spray on the lubricant in a Freon solution, and then you wipe off the excess,
So when we started to put ZDOL, we had tremendous problem trying to spread this around. We did like what the oxide people were doing. It was a spray mist with in the Freon solution, and then you wipe it down. And it was literally done by hand. It was a little product, the TexWipe. It was a TexWipe wand. It's a cotton swab stuck on the plastic. And you wipe it down.
I remember trying that. Basically, you look at it, it looks de-wetted. And that's the problem with the really much any functional group on a lot of these surfaces. The functional groups go down, bond it, and they put a very hydrophobic surface up, very low surface energy up. The next model layer of lubricant comes down, it sort of says, well, I don't want to sit on this thing because it says there's no end groups for me to do my bonding with, so I'm going to ball up and form de-wetting droplets. So if you put on too much, it just de-wets it, and as you wipe it, it just smears it around. Whereas the Krytoxes and the Formulin YR, they would spread out very nicely, right? And the surface tension would pull them flat. Right. But it'd be fairly thick, like I sort of said on particulate disk, it'd be like 50, 60.
So this ZDOL with the end group would get all mucked up as soon as you try to wipe it. And it turned out that you had to apply tremendous amount of force in trying to spread it around. So this was another innovation trick that Tu Chen came out with. So the mist that we were using wasn't fine enough. So he went to his wife's perfume bottle, emptied it, and he had to find enough mist. that was one key step. The second step, instead of using Freon, he decided to mix some methanol into it. And this was kind of an interesting idea too, because when you mix the methanol and Freon, they do mix together, but when they evaporate, the Freon will go first. And the lube is not dissolvable in methanol. So you get these little puddles of methanol, and the lubricant molecule is kind of spread in between, you see. And it provided just enough liquid. It's like a, what's the word for it? It's like an immiscible mixture of lubricant, emulsion of methanol and lubricant, and that allows you to wipe it down. So that was all done by hand, and you know we had just banks of these high torque motors, and we had operator ladies, you know, you just spray and then you wipe them down.
So how long did that last?
6 months until our automation group came up with the equipment to do this, you know.
What about, I mean, more toward, when did you switch over to, say, dip coating or something else?
Oh, that was a long time later.
Long time.
We couldn't make the dip coating work.
Okay.
And this is kind of a, you know, side story, but there's probably a reason why we couldn't make it work. This buffing, we call it buffing because it kind of resembled putting wax on a car. You know, you get this little sort of a mess, and you gotta just use a machine to buff it, you know, until it gets very, very clear and slick. It behaved exactly like that. Once you do that, the surface was really slick. So when we were doing this wipe down, we put so much force on the disc that the disc was literally pretty hot. So we were applying heat on top of it, right? And we had no idea how it was getting on the surface. So it was a combination of this polar lubricant and this buffing process, you know, mechanical force to put the lubricant, and that was kind of a secret for a long time.
But I mean, IBM, by the time I joined the storage function in '87, they were already doing dip coating on thin film media. So
yeah, so it seems like the whole industry had converged into, you know, ZDOL, mostly by deep coating, and that seemed to have addressed most of the reliability issues with stiction, wear, etc. But I think two things happened, right? One thing is that people moved away from a mechanical texture with a rough abrasive, but using a laser, pulse laser, to create the little dots on the landing zone. But also IBM started to move away from landing on the disk and moving the head out of the disk to on power off. So since Matthew, you were at IBM, could you tell us that transition and perhaps what other problems started to happen then?
Okay, like I was saying before, like when for the thin film media, initially they were doing landing on the ID, right? And originally they would texture the whole disk surface to get the right sort of stiction values in the landing zone. After a while, they sort of say, well, out in our data zone where we're reading and writing information, we don't want it to be that rough because of this clearance problem, right? But we want to keep the roughness in the landing zone. So they'd do one texture first on the data zone, and they needed some texture there to get the magnetics to grow, with the magnetic film to grow. They would texture it a particular way with the circumferential texture, so all the domains lined up in the right direction. And then in the landing zone, they go do a separate roughening up process with an abrasive to get the right, much rougher surface, so when the slider landed on them, they wouldn't have the stiction problem. And they'd have to spec these differently, and they would actually add cost, right, because you have to do the separate texturing zone, and you lose to do the transition out. And the other problem they would have, okay, they can fly all right in the data zone. When they come back to the landing zone, well, then now this roughness is higher than their fly height, so they'd actually grind a bit as they landed in the landing zone, right? That create wear problems for them, right? They solve the stiction problem by making it rough, but of course now it's very rough there, and that roughness will be an abrasive on your head as you come in and land the power off, or when you try and spin up to get flying out into your data zone. So this is a very unsatisfactory situation, right? And in a way, my boss Brian Stewart said sort of like this is kind of Stone Age technology because you're using an abrasive to texture this up. And at IBM Research, there's Andrew Tam and various other people like Tao and Wen knew about. Andy Tam particularly was a very expert on laser processing and manufacturing. He was in manufacturing research at that time. So I think these guys came with hey, maybe we could do a pulsable laser and sort of create a little bump on the disk surface, and that by putting an array of those, we can then custom tailor the landing zone with not this rough mechanical texture that's kind of uncontrollable, but sort of a very precisely defined texture with the sort of bump, which has a nice round curvature on it, which much less abrasive against the head, right? And we can sort of, by dialing in the energy here, change the height of the bumps, so we can sort of set that so the optimum value for stiction and get a nice, good, uniform control over it.
So by the way, just FYI, the IBM thinks they invented laser texture, but as I was at Seagate at the time, I think laser texture was invented by Control Data. The original patent was from Rajiv Ranjan at Control Data, working with some CMU professor. So just
Dave Lambeth.
Dave Lambeth, exactly. So the original patent was theirs and not IBM.
I'm sure Andrew Tam was probably aware of that, and that's probably what motivated him to pursue this. My boss, or the various bosses were looking for, hey, how do we solve these stiction and wear problems that are coming from our rough landing zone, right? And this was kind of an elegant way of doing that, where as Brian Street said, get it out of the Stone Age into the modern age, right? So using laser texture, right? So
and that worked out okay, right?
Well, I mean, it took one thing, I wasn't directly involved in this, but it took them quite a few years to sort out all the issues of how do you set up the laser system? How do you make it manufacturable? How do you optimize it, right? So, and quite a few people got involved at that stage. I played a small role in sort of like how do you characterize these laser texture bumps.
How about at Komag, Tom? Did Komag also use laser texture?
I think we should backtrack a little bit. Initially, on the magnetic side, there were the two ways of doing it in the sputtered thin film, and one was called the oriented media process. This was invented by a guy named, or discovered by a guy named L-Tukey, IBM. Atef L-Tukey. And by doing a circumferential texture on the disk, and he put chrome on first, and then put the magnetic layer on top of it, you get this sort of orientation effect. A lot of debate as to what that was, crystallographic or stress-related. Anyway, you get this orientation of magnetic moment circumferentially, which is very beneficial for recording. So, but I think the reason why he put the media on a circumferentially textured disk was it was put there for tribological reasons. Right? It was to solve this stiction issue. So he just I think, this is my speculation, but I think he just happened to have that kind of substrate. So when he put this chrome underlayer process, he observed this orientation effect. So right away, he formed a company called Trimedia. It was a competitor to us, from very beginning. We started about the same time as Komag. And then, but the Komag magnetic did not require orientation. It was isotropic. So we didn't have chrome underlayer So the texture was there strictly for the purpose of stiction. But for the oriented media folks, initially this orientation effect would not happen unless you had a fairly rough texture, and you needed a fairly thick chrome. So for a while, the texture required for this orientation effect was much greater than what would have been needed for stiction reasons. So we thought that we had a definite advantage because we could make texture or roughness much smoother, right? And so we even could put the texture just on the landing zone at the ID. So we had a product like that for a while as well. But eventually the oriented media process got to a stage where texture was much smoother, more smoother than it was than required or needed for stiction issues. So that's when the idea of laser texture started to make sense, right? So actually, I knew about the laser texture because I hired Rajiv Ranjam from CEC. When I hired him, he said, well, this is what I've done, is laser texture. And I thought, wow, this is interesting. But I didn't think it was really practical at the time because, there's so many things that could potentially affect it. And it does, nature of the nickel phosphorus surface, cleaning condition, and just.
I know at IBM it took a long time to sort out all these issues.
Yeah, it's tough, So to my surprise, Rajiv goes to Seagate, and now, long before that, Seagate purchased all of CDC and ends up with their patent portfolio too. And there it was, the laser texture. So, Seagate was one of our customers, and one day, to our surprise, so we're going to go do this laser texture, right? so if you're going to sell us the media, you have to have the same. So we had no choice but to develop it ourselves too.
Yeah, I remember I was at Seagate when Seagate purchased Imprimis, the division of control data, yes. And my boss's boss went to the first technical exchange back in Minneapolis and came back and laughing, saying, do you know what these guys are doing? They're crazy. They're trying to do laser texture. They're trying to do texture with a laser. It's such a stupid idea. And I said to myself, that's not such a stupid idea. I love that idea. And then, yeah, sure enough, 2 or 3 years later, every disk was laser textured. Yeah. So did laser texture bring new problems? Did it solve problems, Tom?
I think it was superior. My personal opinion, for tribology reasons, and but the implementing it was much more difficult, of course. Developing the tool itself, the system that has a stable enough laser, and be able to control the power and vary it and so on. We had an incredible laser expert in Komag. So we were able to create our own equipment very, very quickly. Within 3-4 months, we had a tool. But once we started to try to apply it, it turns out your plating conditions and so on definitely had an effect. How you clean it had an effect. How long you wait between cleaning to the laser texture had an effect. All kinds of issues like that you had to control.
And I think some of the science coming out of IBM explain all this.
Yeah, the team there worked quite extensively on all these issues. And I understand the science, that's one thing IBM was always very good at, was sort of, we had this research division that would sort of, wouldn't feel comfortable with a new technique unless it understood a fair amount of the science behind it, right? So. They did a lot of science of understanding what formed these bumps, the form the different shapes that you would see. Yeah. And from my standpoint, at that point, studying the lubricant. Okay, here's a nice, well-defined geometry for the the study here as well. So I think the same thing that's when you were at Seagate, Bruno, right, is you sort of say, okay, hey, we can really analyze stiction and the side up front, what sort of heights you want on the bumps and what sort of distribution.
Yeah, and as usual, we just read the IBM papers and learn all the science behind the empirical measurements we would make.
Very good about publishing the work because my boss's philosophy is if you want the smartest people, you got to let them publish. Whereas if you at Seagate, they probably didn't let you publish, and that's why you left to come to IBM, right?
So so there was another transition where all of a sudden IBM said, okay, we're going to stop landing on the disk. We're going to put the head on the outside of the disk, and that was driven mostly by mobile application and putting drives in laptops. So could you maybe tell us about this?
Let me show here. Right, this is the drive I showed you before. When it was powered off, it lands here. Whereas this one, when it powers off, it lands out here off the disk. And there's the white here is this load-unload ramp that sort of when the disk drive spins up to speed, the slider comes. This actuator pushes the slider onto the head, so it comes down the ramp, develops its fly height, and right away goes off there. So it never has to actually land on the disk and grind against it. That lets you just do the texture across the whole disk for the data zone. You don't have to do any separate texturing process. So you lose the cost of making the texture zone, but you gain the cost of the load-unload ramp.
And was it done primarily for reliability, for shock performance, maybe?
There are a couple reasons. One was when you're out on the ramp here, you don't worry so much about shock anymore, right? Whereas if you're landing on the data zone for a mobile drive, if the drive gets dropped, there's a risk that when it hits the floor, the shock will bounce the head off the disk and come back and slap back down again, right? So whereas on the ramp, you're kind of safe out there. So when you power off, and the other reason, which is probably more important, is that when you're on the ramp, it takes less energy to spin the drive. So most of the time when you're working with your laptop, you're not really reading and writing through the disk. So what you do with the load-unload is when you're not reading and writing, you go up to the ramp and wait for the read-write command. And so I go up there, I'm losing less power to spin the disk to have it ready here, right? So, so the fairly significant power savings or energy savings on your battery if you can have a load-unload ramp compared to.
And maybe you can use a motor that's cheaper because it doesn't have as much torque. Okay.
That's another one. Like say, it's a cheaper motor for the less torque to do the stuff. Because that's what they used to do is that if you did at a landing zone, when they're not reading right, they go and land there. So rather than being 20,000 stop starts, you're up a million stop starts that you have to potentially worry about, right?
So IBM developed the technology for mobile application, the small disk drive, and then they decided to apply it to even desktop and server class disk drives. Is there a reason for that? There's all these trade-offs there, but one of the key reasons for going to load-unload and other products besides mobile is you can standardize on one technology. You don't have to, when you say, okay, I'm developing a stop-start for the server products and a load-unload ramp for here. Let's just go all load-unload. Since we need that in the mobile drive, you might as well go have it in your server product. So my research and development costs will be less, right? So that was final reason for doing it. But I think they also like these other advantages as well in terms of not having to put the cost of a laser texture zone on, not have to worry about those issues. And so all of a sudden you don't have the stiction problem anymore, you don't have the start-stop problems anymore. Did that create more problems, or did companies then went all out and lowering spacing and creating more problems?
The problems you get with load-unload is that you come down this ramp, if you don't, sometimes the transition isn't always smooth. Sometimes a corner of the slider will gouge into the disk, so you have to sort of design your system properly so that you don't contact the disk with enough force that gouges that there and damage your disk. And there are various ways people do that. I know Western Digital's philosophy was we're just going to do a good mechanical design. IBM's philosophy eventually became, well, we're going to have all our disks be glass substrates. And glass is much tougher for these sort of head impacts out and when it comes down the ramp and contacts for the disks out there, right? So you get a lot fewer gouges there. You meet your spec that way. So that was another way, that drove the standardization to, at least with an IBM, and I guess maybe at that point Hitachi, was the, hey, let's go to glass substrates for all the products. Where I think Western Digital, I don't know what they're still doing, is we'll have aluminum, magnesium substrates for a lot of their disk surfaces, even in mobile products.
So Tom, tell us about the transition from CSS to load unload.
I always kind of wonder, well, why didn't the drive guys do this much earlier? If they had, we wouldn't have had all this tribology issues to solve. I mean, a good amount of our resource was put on tribology issues, in terms of people, R&D resources and whatnot, So I think it was great that it was done because not having to land on the disk, solved so many issues. Now, I think all of that was made up for by just pushing the fly height much lower, which probably caused other issues to pop up, But
yeah, so there have been a couple of more iteration in lubricant technology, right?
Yes,
so could you tell us whether at some point ZDOL didn't work anymore? And
we used ZDOL for a very long time. Not that we didn't try, but it just worked really well. And but eventually, one key change was the addition of phosphazine additive X1P. This was to deal with the lube breakdown phenomena that was being observed, and I think like IBM, probably Mathew, you worked pretty hard on that too, right?
Well, I know the problem very well.
Yeah, and this occurs. It was observed that like the alumina, these kind of ceramic type of material, can cause lube like ZDOL to break down, and the thin film had this aluminum oxide, titanium carbide composite material, and this was probably one of the big reason why such things were happening. And this breakdown phenomena, I think, started to be observed when you start going lower and lower flight height. And this phosphazine molecule, as an additive, prevents the breakdown of the lubricant. So we had to start putting that in. And I think some of the dry companies doing better. Maybe there was some other contaminant involved in the issue too. But the thing that we hated so much about the phosphazine was that these guys that were making it wanted per disc royalty. I don't know. They got very rich doing this.
It was a cent or 2 cents per disc or something.
Yeah, a couple cents.
Couple of cents.
But there was a lot of discs being made.
Okay, yeah, and let me just give a couple of backstories to what Tom was saying here. You talked about the sliders, sintered aluminum oxide and titanium carbide. And the backstory on why that was chosen was it's a very hard material. That matches the hardness of the aluminum oxide particles in the old particulate discs. And you might ask, well, why didn't you switch to something else when you went to thin film media where there's no longer aluminum particles in there? Well, basically because all the manufacturing lines were set up to handle and make sliders and recording heads off of what's called N58, which is the name for this sintered aluminum oxide titanium carbide. The problem with aluminum oxide, particularly within these slider heads, and this is the same thing was on the particulate media, this aluminum oxide was called a Lewis acid site. And it turned out for these proliferate polyethers, if they're a linear branch chain like in the formulin ZDOL molecule or the formulin Z, is that that's very sensitive to these Lewis acid sites that causes degradation there by breaking the molecules apart, and they react and they go off and form these what's called degraded lubricant, which is sort of gum up the works basically inside of a disk drive. And the way IBM had a little difference, the Tom say how they had to use X1P and pay the 1 or 2 cents per disk that the company was charging there. Whereas IBM solved this problem by putting carbon overcoats on their slider very early on, and that would sort of coat the aluminum oxide on the slider surface. And I actually knew the guy who came up with putting carbon overcoats on the thing. He didn't set out to do this, but he noticed that if he used sliders against a disk, they would get coated with carbon, and that would actually go, if you go off and start a new test with them in a stop-start test, that improved their durability, largely because you had the carbon overcoat on there, which wouldn't degrade the formalin-Zeedol lubricant, right, that they were using in the thing there. So we were able to solve a lot of the tribology problems by very early on putting on carbon overcoats on our sliders, which I think the rest of the industry went to when they went to MR heads for protect it from corrosion, right? But IBM never had to put X1P and pay the royalty on that because hey, we don't have this problem that these guys are solving with this.
So the thing that made it even more frustrating for Komag was that we had a head company also, Dostek and Headway, and there what we noticed was that how you lap these sliders made a huge difference in the way the tribology worked. So what was happening was that these sliders they're lapped, and if you don't do it properly, the surface sheds particles, and a lot of it was aluminum oxide. And so, for example, you took a poorly lapped head and just sort of bang it on the disk. We had created a specially rough disk and just kind of run it for a while, and then use that surface to do the contact start-stop test. Get fantastic results. Which kind of says that a lot of the problem wear and this loop breakdown is caused by the head guys, right? Get them to fix their problem, and you won't.
Well, this is you work for a disk company, so all your problems were always the head guy's fault. When you work for the drive company, which has both a disk component and the head plane, you have to sort of figure out how do you get these two guys to work together, right? And also the mechanical design as well, right? How do you get everyone to work together in the systematic? And that was always
and trying not to point fingers.
Yeah, I mean, it was always our disk is great if you do it properly. Well, our head is great if you change everything you do, right? And I always, oftentimes when they put everything together, they sort of say, well, what's the easiest fix we can do? Well, change the lubricant. So they come to me. I was oftentimes the lubricant guy say, what fixes can you come up with, say by tomorrow or the next day, to solve this problem we've been, so we can ship this product without having to go through another year of redeveloping it to make everything work right,
So getting back to this lubricant change or design, the change in lubricant was one of the most scary things that you could consider. And this is because I think we had a lot of former IBM people, and IBM seemed to have suffered number of problems by changing loops. You put the product out there in the field, and something happens, catastrophic.
Yeah, I remember, there was one of them. I worked in the research part. Oftentimes you have to go down to the development area, right? And for a while there was a guy who was the head of the development area, and the story he would always tell. Well, the last guy who had my job decided he was going to change the lube. He was fired. I guess he went to work for Komag because that lubricant change didn't work out well. So you're going to have to be a tough sell for me to get me. And
the saying at the time was, change the lube, lose your job.
right, that's it comes from this guy who he was had the disc developed for a long time, but he'd always tell anyone who would listen, hey, this is the lesson I learned from my last guy, right? Change. And this is actually, the change in lube was actually on the particulate media. They were trying to, again, I think I mentioned this, go from a branch Fonblin Y to the Z. Well, it didn't work because of the lubricant degradation problem. Yeah. But the Fonblin Z worked fine on the thin film media. But okay, if you got Z-Dol on there, how do you fix the problems and without changing the lubricant too much, right? And so a lot of our work ended up being, well, how do you bond the Fonblin Z-Dol, right, to the disk, right? And people came up with various methods for doing that, with like heat the disk up. You can do a thermal bonding process. At IBM Research, we developed using ultraviolet light the bond the lubricant in the disk, and that was actually used in products for quite a while.
And then at some point, even that didn't work because the fly was so low that lubricant started to transfer to the heads, and so people decided that perhaps the one OH group at the end of the chain was not enough. So can you guys tell me about this?
Well, one thing, I mean, like I said, looking for ways of bonding this lubricant, and like I said, I had to come up with the ultraviolet light and thermal bonding. But those all cost quite a bit, so they were then thinking, what's a cheaper way to bond the lubricant? So the next transition was, let's go to Z-tetrol, which is, instead of one OH group at each end, they had two OH groups at each end of the molecule, so 4 altogether. And that really proved the bonding as measured by a solvent extraction method, right? So, and actually reduced the spin-off as well. So that was a good low-cost solution. But it took quite a while to get there. I remember going down and my boss was saying, oh, what's the bonding mechanism? Well, there's Fonblin's. You can go from Fonblin Z-Dol to Z-tetrol and go, well, that's changed in lube, we're going to
So the tetra has a 4 OH, right? So this is more
right. Yeah, so
much more stronger.
Yeah, so you get
bonding.
You double the bonding strength basically, for very little cost. It's the same dip coating process. Everything looks the same, just doubles the bonding there, right?
So
one thing on this bonding I didn't mention before is that if you remember the plot I was showing earlier, that as the magnetic spacing goes down, the roughness comes down. But as the roughness comes down, you have less wear problems than you once had before. So but you tend to get more spin-off right there. You start worrying more about spinning because you're thinning down the lubricant to start with. So the way you solve that spin-off problem is by increasing the bonding strength, so you get less spin-off, right? So there's actually a connection between roughness, which is going down, and the need for more bonding. Because when it's rougher, you want to have a thicker lubricant to protect against the wear. As you get smoother, you don't need the thickness anymore, but now you're more worried about lubricant spin-off more, lubricant mobility. So you're trying to tamp the mobility by bonding it to the disk. And that also helps on wear in terms of it's tougher to displace a lubricant that's bonded to the disk compared to one that's less bonded.
Mm-hmm. So Tom, did you have the same experience at Komag?
Yeah. So in terms of bonding, we try various things also. Heating. We did plasma etching, to try to activate the surface, if you will, a little bit before applying the lube, that sort of thing. But finally we kind of went on to do a UV curing, and so the idea there was that you could use a certain type of UV wavelengths to basically, I think you're breaking some of the bonds.
Right. Yeah.
You're actually degrading the lubricant to some extent to force it to bond stronger. So we worked with the vendor in Japan to develop the tool, work out the type of lamps, a UV lamp that we need to use. Took over a year to do, I think, but we were able to do this fairly successfully. But again, just like changing lube, I think there was some really bad experience in IBM. I don't know, that there was a huge resistance to using UV. I think it was because UV can cause ozone formation if you don't watch out. And so we had to arrange it so that you evacuate it was nitrogen filled while doing the UV process. And the lamp degrades over time, so you have to manage that too. So there's all sorts of issues. But we were able to successfully convert everything to 100% UV. So that was to increase the bonding to make it a little more immobile, and I think it happened that way because the texture was becoming smoother and smoother. You needed just more bonding was helpful.
Okay, so we talked about roughness, texture. We talked about substrate. We talked about lubricant quite a bit. So one thing we haven't talked too much about is the overcoat. Matthew, can you tell me a little bit about the overcoat on the disk and the various materials that were used over the years?
Okay, yeah, I mean, the carbon overcoat has been the main champ. I mean, I remember when I first joined there, they were looking at all sorts of alternative. I think there was even ones being shipped with zirconium oxide was, I forget the name of the company that was shipping zirconium oxide.
Komag.
Komag, okay. So I spent a few months looking at zirconium oxide, but people really weren't that interested at IBM. Zirconium oxide.
I think some company.
Silicon oxide.
Japan, glass, yeah.
Glass, yeah. So which I'm trying to remember. It was
Hoya.
What was the name of the company? I'm trying to remember how it was deposited. It was some chemical process.
Maybe sol gel or something.
Sol gel type process, yeah. And here, I think, God, I'm trying to remember the guy's name. IBM fellow, Ken something.
Ken Howard?
Ken Howard, that's what I was in.
Yeah.
He was the first guy to do carbon overcoats. And he, doing things. But even before that, the first thin film media had a rhodium overcoat, which that sticks in my mind because rhodium was one of my thesis topics. But that's a very hard inert metal, right? But very expensive, so I think that went out of favor. But the reason why carbon overcoats have always remained the champ is the chemistry is so versatile, right? You can sort of by various ways you can deposit it, even though the conventional way is always by sputtering, but people looked at plasma depositions in all sorts of ways. And then you can add things like hydrogen and nitrogen, and even oxygen, and they try and change the chemistry, change the hardness. So people explored all these parameters, the various degrees of bonding of carbon, the sp2 versus sp3, what's the right ratio there. And so as your products change, you can sort of tweak the carbon process, change these parameters to get the most optimum process for that product, right? So I'm sure when Bruno was at Seagate, he worked a lot with that, right? So,
Tom?
So the carbon overcoat is kind of an interesting history. The first reported paper on carbon overcoat is by a guy named Francis King at a company called Data Point, and this is in I think I'd like to say it was late 70s. It might have been early 80s. Anyway, it was on a plated disk that was deposited on, and somehow I think the drive was for some video recording purposes or something. That's my recollection of it. But that was the first reported in that paper. And I remember when I was starting to work for Tu Chen, when he was at Xerox, he was actually talking about it. So he was aware very, very early on. And most of the sputter company had carbon overcoat right off the bat, and this makes sense because you're doing sputtering. It's just as easy to put something on the same equipment by the same method. So my recollection when we got going, carbon was it. There wasn't anything else that you could was being considered.
At the time, people call it diamond-like, right? As if it
but
was made of diamond, but
yeah,
not
it was
quite.
just for purely sales purposes. I had no idea. No, there wasn't any measurements done. Oh, it's carbon, therefore it must be like diamond-like. As you know, the carbon overcoat, when you sputter, is basically amorphous.
And mostly graphite-like.
It's more graphite-like than anything else. So when we started, it was about, I believe it was about 200 angstrom, maybe 20 nanometers. That was kind of like the beginning. The interesting side story to this is that Tu Chen, when he was putting carbon overcoat on a plated disk for the Century data, and he actually had some tribological testing and so on. And what he told me was that the performance was very, very good in terms of protection, corrosion, tribology, all of that. So I think that's the reason why it was clearly the way to go when he started Komag. But the material that he used, this is all in hindsight, by the way. The material that he used for target was the type of carbon called pyrolytic carbon. It's made by sort of a high temperature decomposition of petroleum product, and the key thing is that it contains a lot of hydrogen. So, but it's very difficult to make, very expensive, and you can't use DC magnetron. It's too resistive. So you have to use RF. And all of those kind of conspire so that you couldn't consider this pyrolytic carbon. But unbeknownst to Tu Chen, what he put on in Xerox was this hydrogenated carbon that he was putting on, which is probably very good for corrosion resistance. But for us, everybody in the industry, in order to sputter carbon, it's got a very low deposition rate. And you need magnetron cathode to sputter this at a high enough rate. And the magnetron requires a very conductive target material. And for that, you use just graphite. This is like an electrode material. It's very porous, but it is very conductive. And that's what we used. But even then, the mismatch between the deposition rate of the carbon and the magnetic layer was just so huge that it took a lot of effort to create the cathode that had high enough power to deposit this even 200 angstrom. I remember that was quite a bit of struggle.
And I think at some point Komag realized that maybe doping the carbon with some nitrogen was helping.
So that was kind of by accident. But before doing that, we were trying to qualify our disk with sputtered carbon to IBM, and we couldn't pass the corrosion test. And I tried everything. We put interlayer of chrome, tantalum, that kind of titanium, try to protect the magnetic layer, and we could not pass the corrosion test. And I swear, we thought that this was on purpose, that there was such a resistance to using thin film media in IBM at the time, that this test was deliberately set to fail. Fail the thin film media. That's what we thought anyway. So we couldn't make it work. That's when we came up with the zirconia overcoat. Ceramic, right? Ceramic material, and it had fantastic corrosion resistance. And so we were able to sell to IBM. Fujisawa made a drive using this. We sold quite a few disks, but only to IBM. And back then they were using ferrite heads. And with the ferrite head, zirconia worked great. As soon as they switched to thin film heads, problems started to happen. And you know what? Again, hindsight, it was lube breakdown. you had the ceramic material, and with the Altec head, had two ceramic surfaces rubbing against the Z-dough. I guess that was not a good combination. But so all throughout, once we developed the zirconia overcoat, the question was why the corrosion resistance was so good, right? It's very, very resistive. Of course, being ceramic, high density material, that helped too. But so that was one of the key things that we had in mind. And now getting back to carbon, as we were making this sputter disk with carbon overcoat, we had what's called an inline sputter machine. The disks to be sputtered were put on the panels. And the panel would go in and out of this vacuum system through a low lock chamber. It would go into the low lock, gets pumped down, goes in, and pass through the cathode. Magnetic layer is put down, and the carbon is put down, and then it comes out of the system. And the finished disk is pulled out, fresh disk put on. And this panel is coming in and out of the sputter system right now. Company like Seagate also had a machine like that too, called inline sputter system. The big problem with this kind of system is that this panel is picking up water vapor each time it comes in and out. And this was affecting not only the magnetic layer, but the carbon layer as well. And we didn't really realize what was going on. So at the beginning of the cycle, we would run this machine for 2 weeks at a time. And all this time, this thick layer of film is building up on the panel. And it's continuously absorbing water. But at the beginning of the cycle, where we sandblast this and wash this thing, and we would dry it, but it was still loaded with water. And at the beginning of the cycle, the carbon was coming out sort of with a yellowish tinge. And then as we go in several days, you start getting grayer and grayer. And noticed that, but we didn't really pay attention until one of our tribology guys says, hey, the stuff you're making isn't performing so well, right? And the disk he had was this grayish carbon. It says, give me this kind of disk. It was a disk with a yellowish tinge. I like this disk better. And I was like, huh. So it was the water that was breaking down inside the sputter chamber, making its way into the carbon chamber that was incorporating hydrogen.
And changing the optical properties as
yes,
well as the
optical
mechanical.
property as well. And so, this is it, right? And then I checked the resistivity. It was definitely much more resistive with this yellowish carbon. So that was the key discovery, if you will. And so I started to get on this experiment mode, to try to pump more hydrogen into the chamber. And it actually took a lot of hydrogen. It was like 20%. That's when we got this beautiful yellowish carbon. We call it the yellow carbon process. And that was the key. And that carbon had incredibly good corrosion resistance, as good as zirconia, and highly resistive. And so that, I think we were one of the first to put out a disk like that. Now, most of the company in the US was using sputtering. But I know that in Japan, they were using PECVD. Right? If you do that, you use like methane or ethylene, this kind of gas, then you will automatically incorporate hydrogen into the carbon film. So, but I didn't see any disk from Japan back then, so I don't know. Maybe they had better carbon from that perspective.
Matthew, you were involved in maybe more of the metrology aspect of carbon film and ways to measure the thickness.
Yeah, the thickness is both on lubricant and carbon. Was always people found that challenging because that people didn't really took a long time to come up with good ways of measuring it. Like I say, in particular media, they had problems measuring the loop thickness. You came with this sort of clumsy AFM method. When you went thin film media, the ways they came up with measuring lubricant thickness was by FTIR, calibrating against an ESCA measurement. And at some point, Mike Toning and I decided we were going to calibrate that versus X-ray reflectivity, which is using X-rays to do a diffraction interference method to measure the lubricant thickness. And at the same time, we also put down some carbon films and measured the lubricant thickness on top of that, and found out we can measure the carbon thickness as well by this technique. And so that's became the sort of standard way of benchmarking other techniques against the this X-ray reflectivity technique. Because the way a lot of people were doing it before, lubricant thickness was measuring the escape depth of the carbon signal through there. And as the carbon film got thinner, they could use the escape depth there, or they use X-ray fluorescent was another technique. But they really had a tough time. How do you go off and standardize the signal you get from these various techniques against some known thickness? One way is just doing a cross section, putting it into a TEM or something like that and measuring it there. But that's kind of not all that accurate. So this X-ray reflectivity measurement came to be a very good way of doing it.
Now the reflectivity signal changes with the density of the material. So
right. So you have to you set up a model with two adjustable parameters. One is the density, the other is the thickness. Right. You have enough because you're going through various angles on your X-ray reflectivity. You get enough information there that you can fit the two parameters reasonably well. But another parameter you've got to model in there is the roughness, which is as things just got smoother, that got easier to handle, right? So
with one measurement, you can get three
things:
roughness, density, and thickness.
And doing it on thin film media, it's a little tricky because then you also have the different magnetic layers as well. You somehow have to throw into your model as well. So, but that all got sorted out. Our initial study was very simple carbon film on a silicon wafer, but once we demonstrated, hey, it worked very well there, it wasn't that so difficult to get it onto thin film media. Other techniques we looked at was ellipsometry was a way we would do these things and measure thickness. But carbon was always the trickier one compared to loop thicknesses. But I know a lot of companies like Komag, there was a lot of debate about how to measure lubricant thickness. And they talk about IBM angstroms versus other people's angstroms. But
as long as there's
once we showed that IBM angstrom was the correct way to go, I think that's resolved a lot of issues.
So we talk about quite a number of things. Lately, in the past maybe 10 years, the industry went to thermal fly height control. Did that change anything as far as reliability, tribology, materials? Tom, were you involved in that?
I think a lot of it happened after I left, so I'm not quite so familiar with all of what went on. It was just starting to be used, if I remember correctly. I mean, with combination with the touchdown sensing. I think that was a pretty amazing feat, in my opinion, to be able to do that.
Yeah, I was amazed at how that it got adapted all, because it's a nice, clever way of adjusting, controlling that clearance. Basically, you sort of say, okay, when I'm not reading right, I'm going to have a high clearance, and then when I'm want to read and write, I'm going to reduce the clearance. And the way you do that is by having a heater built into the recording head. So you sort of heat it up. When it heats up, get a thermal expansion. That lowers the bottom of the read sensor and write sensor down towards the disk, right? So you can actually then do clever things like you sort of say, well, I can go and actually figure out where the disk surface is by going down and touching it and have some signals that tell me when I'm touching on the disk, and then back off a certain distance so I can sort of set the clearance to what I want, or set the magnetic spacing or really what I'm saying is set the clearance at a safe value, right? So where I know I can clear, right? So that sort of really helped on minimizing fly height variation, because I sort of said this thing comes down the ramp here and is designed at a particular average fly height, but not all sliders fly at that high. Some fly high, some fly low. And you can use this thermal control to sort of say, I'm going to get rid of this variation in slider fly height by setting that at the value I want. And that really helps a lot in dealing with, okay, the bad actors in your batch process, right? So if someone's flying too low, well, you just sort of raise the fly height using the thermal control. If one's flying too high, well, you just bring it into the right spec.
So I think it's a huge innovation to do that, because otherwise, for both tribology and magnetic, you have to design for the worst case. For the worst case head that happens to fly a little higher or too low.
Right, yeah.
And the magnetic has to accommodate the highest flying head, right? So the media guy, this is a media guy's opinion, we were getting pushed to accommodate the head variability, right? And this thermal fly height control touchdown sensor, I think that kind of changed the ball game completely.
Yeah. One sort of related thing on that is over the years I counted up, I think it was like 6 or 7 times I'd be on what was called the contact recording process. So the idea is, rather than flying with a clearance, you come down and boost your clearance to 0, right, and try and fly in contact with some sort of interference, right. But what always do the problem in the end was sort of these wear issues, or when you're in contact, it sort of causes the head to bounce around a bit too much, right. So you always want a little bit of back off, and this thing will allow you to do that. But the thermal fly height, to come in and figure out where the disk is, you do get a little bit of contact. So you do have to design for some amount of contact in your system. You locate it to
when you calibrate to touchdown and then back off.
Yeah. And there's always a question. I mean, there will always be a desire. As things change in your drive, like say the temperature or something like that, you'd like to sort of recalibrate. But there's a limit to how many times you can go in there and contact before you've wore off the carbon overcoat on your head, for example, right? So, those 4 wear issues came up. Is how do we design the system so we can have as many contacts as we'd like to have, but without damaging our head, right?
So we're almost through with all of the technical questions. Is there anything else you'd like to add? Funny story, back door stories, things we forgot? Tom, anything you'd like to add?
Maybe a few comments about the lubricant. We didn't maybe finish the discussion there. I think the lubricant used today are basically what I might call a designer lube. They're actually specially made. So we work with a company called Moresco that turned out to be an incredible company, very, very skilled in fluorine chemistry. And so the first kind of a product that they made for us was basically a Z-Dol with an end chain that has X1P on it, built into the lubricant. So, Moresco, I guess they're a company that makes hydraulic fluids, very specialized hydraulic fluid, very small company, but they had this multi-million-dollar NMR, nuclear magnetic resonance. It is absolutely a critical instrument for doing fluorine chemistry, right? So they had that kind of equipment. They had unbelievable distillation and fractionating setup. Never seen anything like it. It's just rows and rows of distillation equipment. Because these fluorine chemistry, I think the key is you manufacture them, create it, but then you gotta size it for the right molecular weight and so on. You really gotta know how to narrow the molecular weight and things of that nature. So they were really, really good at it. And so Komag and WDD went that way to try to kind of custom make a lubricant with some ideas about what you want to do, what kind of end group, how many you might have, X1P, type of molecular weight distribution, and I don't know what they're using today, but I'm sure they're kind of doing that sort of thing, continue to do that sort of thing.
Thanks, Tom. Matthew? Yeah.
Well, I mean, I've got one little story about, we were talking earlier about it, this head of the disk development area who motto was change the lube, he'd lose his job, right? I actually convinced him to change the lube for one product, right? So, and the way this story comes about is that at that time, IBM was shipping their disk with Fonblin with a molecular weight of 2,000 AMU, whereas I think by that point, most other companies were shipping, this is Fonblin Zedol, I should say, they were shipping Fonblin Zedol with a molecular weight of 4,000 AMU, right? So the experiment I did is I took these, two sets of disks, with one with lubricated with Fonblin Zedol 2000, another one with lubricated with Fonblin Zedol 4000, and put them on a hot plate and raise the temperature of the hot plate to room temperature. And every now and then I'd take it off and put it in the FTIR, measure the lubricant thickness, put it back on the hot plate. And after an afternoon of this, I had a nice plot that sort of showed that the disks lubricated with Fonblin Zedol 4000 had a nice constant lube thickness. The ones with Zedol 2000 quickly lost, like a third of their thickness and then plateaued out.
By evaporation.
By evaporation, simple evaporation, at file temperature. And no one at IBM had ever clued into this, So I generated this plot, drew it by hand because we didn't have a graphics program back then. And at some point showed this to this the head of the disk development area. Hey, look at this plot here. And he said, oh, it's a great plot. And he goes off and starts showing it around. And within a month, they switched the loop from Zedol 2000 to Zedol 4000, right? So,
and nobody lost their job.
No one lost their job. It was just really a few hours work on my part. I had a success for my year of the end performance. Hey, I changed the lubricant. No one's done research that's ever done that before.
That's great.
So this concludes our interview. So thank you very much, not only for your contribution to the technology and the disk drive, but also for being good sports and accepting to be interviewed today. So thanks very much.
Thank you.
Thanks very much.